Lightning is one of the most spectacular and at the same time one of the most dangerous natural phenomena we can witness on Earth. And although people have observed it since ancient times and many early civilizations tried to explain it as the anger of gods or a sign from supernatural powers, we now know it is the result of a complex interplay between meteorology, physics, and electricity on an enormous scale, happening in an incredibly short time. To truly understand how lightning forms, we need to go deep inside a thundercloud, which itself only takes shape when the atmosphere brings together very specific conditions. Everything begins with a thundercloud known as a cumulonimbus, a towering vertical cloud formation that can rise more than 35,000 feet into the sky, reaching the upper layers of the troposphere and in some cases even brushing the lower stratosphere. Such a cloud forms when warm, humid air from the surface rises rapidly due to strong convection currents. As it ascends, the air cools, water vapor condenses into liquid droplets, and latent heat is released, which further fuels the upward motion. At higher altitudes, temperatures drop well below freezing, causing some droplets to freeze into ice crystals, while others remain as supercooled water. Inside this massive cloud, chaos is constant. Powerful updrafts carry lighter ice crystals upward, while downdrafts push heavier hailstones and grapple downward, leading to countless collisions between particles of water, ice, and snow. These collisions cause friction and the transfer of electric charges, and according to the most widely accepted scientific theory, larger ice particles like hailstones tend to gain a negative charge and sink to the lower regions of the cloud, while smaller ice crystals acquire a positive charge and are lifted toward the top. This process, called charge separation, creates a strong electric field inside the cloud, with a positive pole at the top and a negative pole at the bottom. Because electric fields extend beyond the cloud itself, they also influence the ground below. The negatively charged lower portion of the cloud induces a positive charge on the Earth's surface directly beneath it, a process called electrostatic induction. Under normal conditions, air is a very good electrical insulator, preventing the free flow of electrons. But as the difference in electric potential, the voltage, between the cloud and the ground increases and reaches several million volts, the insulating properties of air break down and its molecules begin to ionize, creating a conductive path. The first phase of a lightning strike is called the stepped leader, which begins in the lower part of the cloud and propagates toward the ground in a series of discrete steps, each about 150 feet long, with microsecond pauses between them. The stepped leader is usually invisible to the human eye because it emits relatively little light, but it is crucial for preparing the main channel for the massive discharge that follows. From the ground, especially from tall objects like trees, buildings, or radio towers, upward streamers of opposite charge can rise to meet it. When the stepped leader and an upward streamer connect, a continuous conductive channel is established between the cloud and the ground, and almost instantly a powerful return stroke occurs. This return stroke is vastly brighter and stronger than the leader because it carries an immense current, typically around 30,000 amperes, though extreme strikes can exceed 200,000 amperes, and releases a tremendous amount of energy in just a fraction of a second. The air in the lightning channel heats to about 54,000 degrees Fahrenheit, roughly 5 times hotter than the surface of the sun, and this rapid heating causes the air to expand explosively, creating a shockwave we hear as thunder. Because light travels much faster than sound, we see lightning before we hear thunder, and by counting the seconds between the flash and the sound, we can estimate the distance to the strike, about 5 seconds per mile. Not all lightning strikes hit the ground. Many occur within a cloud, between 2 clouds, or as upward lightning from tall structures. There are also exotic upper atmosphere discharges, such as red sprites, blue jets, and elves, which occur high above thunderstorms and were only scientifically documented in the last few decades. The energy of a typical lightning strike is immense, often around 5 gigajoules, equivalent to the explosive power of roughly 1 ton of TNT. Even though a lightning strike lasts only a few milliseconds, it can start wildfires, damage infrastructure, or cause injury and death, not just from a direct hit, but also from side flashes or ground currents. This is why the safest place during a thunderstorm is inside a substantial building or a car, which acts as a Faraday cage, directing the current around the occupants and safely into the ground. Lightning also plays a role in Earth's ecology. The high temperatures during a strike cause nitrogen and oxygen in the atmosphere to combine, forming nitrogen oxides that dissolve in rainwater and act as a natural fertilizer, enriching the soil. So, a phenomenon that can be deadly to humans is also a vital part of the planet's natural cycles that support life. Next time you find yourself under a dark sky and see it split by a brilliant flash, you'll know the intricate chain of events that had to occur. From the chaotic dance of ice crystals and hailstones inside a towering storm cloud, through the buildup of immense electrical potential, to the moment when air itself becomes conductive and nature unleashes a burst of energy comparable to a small explosion, all in the blink of an eye, in one of the fastest and most spectacular demonstrations of physics our planet has to offer. Subscribe us for more videos.